So today we'll see the tutorial for the stability week. So again, the outline of this tutorial is arranged in such a way so that whatever the theoretical results we have discussed during the whole week, we will see the direct application of those detailed results. In addition, we have also written the slide number as well so that you can refer to the theoretical results while applying those results to solve some problems. So we'll start with the solvability of Lyapunov equations, BIBO and internal stability, questions related to the Lyapunov theory for linear systems. We will also see the margin of stability, which we have not discussed in detail during the lecture. Then we'll see the stability of linear time variant systems, followed by the sampling and stability. This topic was also not covered explicitly during the lecture week. And finally, the stability or knowing some relationship between the stability and the Jordan canonical forms. So the problem first deals with the solvability of the Lyapunov matrix equation. So while one of the key results in the stability, we had seen that Lyapunov equation played a key role, and it hinges on to compute the matrix P given the matrix Q. So here we will see that how you can compute that matrix. During the lecture slide, we had seen one formula which requires the computing one integral. So if we do not want to compute the integral and we just want to comment on the solvability of the equation or computing some P matrix for a given Q, so this problem deals with that issue. So here we consider a linear system which is a homogeneous with the state matrix A 0 1 minus 1 0. So here we need to comment on the solvability of the Lyapunov metric equation, which is given by this one. Now note that here in the stability result concerning with the Lyapunov equation, Q was chosen as a positive definite matrix. Now here we have chosen Q as a semi-definite. So we'll see in the solution that what is the significance of selecting the Q as a semi-definite matrix. So here recall the lecture slide number 22, where for a square matrix of dimension n, and having the eigenvalues lambda 1 to lambda n, eigenvalues of A, then the equation has a unique solution of P corresponding to each Q. Now note that here Q is again selected as a positive definite. So in the slides we discussed or we focused mainly on the positive definite matrices. So corresponding to each Q, if and only if the eigenvalue of the matrix A is not equal to 0. In addition, the summation of the two distinct eigenvalues, or in fact two similar eigenvalues, should not be equal to 0 for all I comma j. So if you compute the eigenvalues of the matrix A directly, you would see that it is on the imaginary axis plus minus j. So therefore the required condition is violated. So we can say that the Lyapunov equation, which was given by this, does not possess a unique solution for a given Q. Now we wanted to comment onto the solvability only for a semi-definite matrix, but we had seen that if Q had been chosen as a positive definite matrix and if the eigenvalues are lying on the imaginary axis, then it does not possess a unique solution. Now let's consider a case where Q is a semi-definite. So we directly select Q as a 0 matrix, and if we start solving the left hand side of this Lyapunov equation, we would have A transpose P plus P into A. So all the matrices A matrix and its transpose are written in or are substituted into this equation. And for computing the P matrix, we have used symbolic variables P11, P12 and this P12 as well, because it is a symmetric matrix, and P22. So substituting these values, we obtain that we can compute the solution for P's which are given by P12 is equal to 0 and P11 is equal to P22, meaning to say there exists a solution for a semi-definite matrix. Now suppose, therefore, for any A belonging to a set of real numbers, the matrix P is equal to AI is the solution of the Lyapunov metric equation. So the consequence of choosing Q as a semi-definite matrix, we see, though it does not possess a unique solution, because for different A's we will obtain different P. But being a semi-definite matrix, we can ensure that there exists at least one solution. Okay. Now choosing Q as a strictly positive definite matrix, you would see once you start solving for all the Pij's, you would see that we obtain P11 is equal to P22 and P12 is equal to 1 and P12 is equal to minus 1, which is not possible. So for Q is equal to 2y should be 2y. The Lyapunov equation has no solution at all. Right? The problem 2 deals with that given continuous time linear time invariant system where the A matrix is a square matrix of dimension 3. Similarly, the B matrix is 3 cross 1 and the C matrix is 1 cross 3. So again it is a single input single output system with initial conditions given as this. So so note that here that x3 is given in terms of the initial condition of the second state. So we want to analyze the system separately for the internal stability and also for the BBO stability. If we write explicitly the dynamics of that state space equation, we can write three different equations, one and each for the different states, x1 dot, x2 dot and x3 dot. So if you see the first equation, first the state of or the right hand side does not contain any x2 and x3, so we can separately solve this equation for x1, which has been done here by using the variation of constants formula. Then putting those x1 or using those x1, we can compute this x2 and x3 separately for the given initial conditions. Now computing yt, which is nothing but the summation of the first two states minus the third state, we obtain final this result. So you would see that we can show that given a bounded input signal, u being a bounded signal, we would obtain a bounded output for all time t. So this system is clearly a BBO stable system. Now checking for the internal stability, which requires to compute the eigenvalues, you would notice the eigenvalues of the A matrix are computed as -1 and -1 and 3. Okay? So it is clearly visible that because of one of the eigenvalues being on the right hand side, the state space system is not at all stable in the sense of Lyapunov, as one of the definitions we had introduced during the lecture week. Now one important conclusion we also made during the lecture week while discussing the relationship between the BBO stability and the Lyapunov stability, whether the both ways implication holds, that if my system is BBO stable, does it imply that it would be internal stable? Or if my system is internal stable, my system would automatically be BBO stable. Now with this example, we have seen that the state space equation is BBO stable, but it is not internal stable. So this implication would hold true, while this implication won't hold, so which is a false. So here we have written this external stability. By external stability, we actually mean the BBO stability, because we also call this external stability because we are dealing with the external signals u and y, not with the internal signals, which is the state. So that's why we call it the internal stability. Okay. The problem 3 deals with that assume that the origin of the system, which is a homogeneous system given the state matrix A, is asymptotically stable. So we know that all the eigenvalues of this matrix lie on the left hand side. Then we need to show that the matrix A is similar to another matrix A bar, which satisfies that A bar plus A bar transpose is a negative definite. Okay. So this question can also be formulated in other words, that is to say that the system is equivalent by a linear change of coordinates to a system in terms of the state denoted by Z with the A bar state matrix, for which the Euclidean norm is strictly decreasing along non-zero solutions. So if you recall that the Euclidean norm, it is equivalent to computing the two norm of the matrix or the vector. Okay, so let's see the solution to this problem. So here you should recall the slide number 30, which discusses the Lyapunov theory of stability for linear systems. So recall that since the matrix is A, it's Hurwitz, saying the matrix A being Hurwitz, meaning that all the eigenvalues are on the left hand side. So there exists a positive definite solution to this equation given a positive definite matrix Q. Okay. Now this Q can be selected any positive definite matrix. So we have selected that I. So there exists any P, which is again symmetric and positive definite, satisfy this equation. Okay. Since the matrix is already a stable matrix, so the Lyapunov equation would hold for the given Q and P. Now once we have computed the P matrix, we can define another positive definite matrix, let's say S, such that S square is equal to P. Now we can also write S is equal to the under root of P, and we shall call it the positive square root of the matrix P. Why the positive square root? Because we know that if whenever we are taking the square root of any positive number, so the square root could be either on the positive side or on the negative side. But we are specifically taking the positive square root, and we call it this matrix as a positive square root matrix of the computed matrix P. Now using the property of the symmetric and a positive definite matrix, we say that this matrix P to the power 1 by 2 is invertible, and we can write this matrix as P to the power minus 1 by 2 as the inverse of the square matrix itself. Okay. So multiplying 1 on the right hand side and on the left by P to the power minus 1 by 2 and rearranging it, we obtain this equation. So see if we can see this step in more detail. So starting from this equation, if I multiply P to the power minus 1 by 2, and here I would have A transpose and P into P to the power minus 1 by 2. Right, this is the first term. The second term is P to the power minus 1 by 2, P A, again P to the power minus 1 by 2, plus the multiplication of P to the power minus 1 by 2 by itself would yield P to the power minus 1 is equal to 0. Okay, now we combine these two terms, which yields P to the power 1 by 2, which is this term. A to the A transpose would stay as it is, this matrix as well. Now on the second term, we would have the P to the power 1 by 2 A matrix, and this matrix would stay as it is. Now we take this P inverse onto the right hand side, writing minus P inverse. Okay. So we note here that since P is a positive definite matrix, its inverse would also be positive definite. So the right hand side would definitely be a negative definite matrix because of the negative sign. Now with A bar defining as this complete part, we see that A is similar to A bar, and A bar plus A transpose is less than 0. In fact, you can see that the A bar is nothing but similarly algebraically equivalent to this matrix A. which is related by non-singular transformation matrix p to the power 1 by 2. Okay. So this completes the proof of this part. In the problem 4, we see that given a positive number sigma and Q be a positive definite matrix and a matrix of the same size as Q, show that if there exists a positive definite matrix P such that it satisfies this equation, then every eigenvalue of A satisfies that the real part of the eigenvalue is less than minus sigma. So you would notice here that if this part is not there, then this equation is nothing but Lyapunov equation. Now, and we know that for a given positive definite matrix Q, if there exists a positive definite matrix P, then the A matrix would be a stable matrix. That is to say that all the eigenvalues would be on the left hand side if this part is not there. Okay. Now with the addition of this part, what we need to show now, or what it implies, that the eigenvalues of the A matrix are also shifted towards the left hand side. Okay, or let's say the axis, the 0 axis is shifted to the left hand side. So the results which we discussed in the lecture slide 30, by using those results, we would going to show that the axis has been also shifted towards the left hand side by adding this term into the Lyapunov equation. So here we would going to use the quadratic forms and the metric norms which we have introduced during the lecture week. So let lambda be a possibly complex eigenvalue of the matrix A and V be the corresponding eigenvector. Right? So we know already that for associated to the eigenvalue A, the eigenvector we can represent as AB is equal to lambda times V, where V is the eigenvector associated with the lambda. Now using the equation, we write the quadratic form, which is V star. V star is the complex conjugate of the vector V, and this complete matrix which is on the left hand side into V. Now we know that this equation already holds, so I can write on the right hand side also minus V star QV. Now using one of the, so if I write this part only, we would have V star A transpose P. Now another way of writing this part, or in fact I forgot this one, so we would have this part also if I open this bracket. So specifically this part I can write as the complex conjugate transpose of the matrix of the vector A into V. You can see this equalization transiting from this part to this part. The rest of the part would remain same. Plus V star PA into V plus I can, because sigma is a scalar, so I can commute with the vector. So I write 2 sigma V star P into V, which is equal to the right hand side as it is. Now using this equation, since it is a complex conjugate transpose, it would become the complex conjugate of the lambda as well. Lambda bar V star PV. Similarly, AV could also be replaced by this lambda V. Again, lambda is a scalar, so I can commute. So we would have V star PV, and similarly onto the third term. Now if I take the common part, which is V star PV, onto the right hand side and group all these scalar values, which is lambda bar plus lambda plus 2 sigma. Right? So what do we need for this matrix to be stable? That the right hand side of the above should also be negative definite. Now this would become negative definite if this scalar is less than 0, is on the left hand side. Now if I combine this lambda bar plus lambda, it becomes twice the real part of lambda, because lambda bar is a complex conjugate transpose of in fact the complex conjugate of the lambda only. So I would have that lambda should be less than minus sigma. And since lambda was an arbitrary eigenvalue of A, so this is O, then every eigenvalue lambda of A must satisfy that lambda should be less than minus sigma. Okay, so this completes the proof of this part. So one important conclusion you should note here, that if we add this term into the Lyapunov equation, the key implication is that all the eigenvalues of A would also be shifted to, or would also be shifted towards to the left hand side of that scalar parameter introduced in the Lyapunov equation. Okay. So the problem 5 deals with the stability of linear time varying systems. So consider the system, the homogeneous system once again, where A of t is given by this matrix, which is a time dependent matrix. So we want to analyze this system for stability. So this equation is this question is based on the lecture slide 57, where if I quote one of the statements from that slide, that the fact that it is not possible to comment on the stability of a linear time varying system by merely computing the eigenvalues of the state matrix. So far, if my system is an LTI system, we have been determining the stability by computing the eigenvalues. Now if we want to apply the same concept to a time varying matrix, we had established that using the eigenvalue concept, you cannot determine the stability of a time varying system, though it is linear. So we will see that how you can compute determine the stability. So for each t, this you can do a very quick test, that using this A of t matrix, first of all compute the eigenvalues. So you would notice that the matrix has a repeated eigenvalue on -1. Now according to that concept, we see that the matrix or the homogeneous system is a stable system. But if we pay attention towards its computing the solution, so we see that x2 can be computed explicitly, and by putting x2 into the first equation, we can compute x1. So x2 trajectory is a stable trajectory for every initial condition, right? But if we pay close attention to x1t, because of this part, since it involves the positive powers of the exponential, we see that the x1 trajectory will reach towards infinity as t tends to infinity, meaning to say that this system is not stable, because if this system is happen to be stable, both the state trajectory should reach to 0 as t tends to infinity. While performing the eigenvalue test on this homogeneous system signifies that this homogeneous system is a stable system. So eigenvalue test is not applicable for time varying systems, and we need to, or one way is to compute the solution. So this problem is an interesting problem, where we would utilize some concepts which the discretization concept we have introduced in the week 1, that we want to compare, or first of all we want to determine the stability of the LTI system given this A matrix, and we want to compare the stability once the system is discretized. Now we had separate tests for determining the stability given a continuous time system and a discrete time system. Now the problem here is that we are provided with a continuous time system. Now if we discretized it using the methods we have introduced in the week 1, we want to verify that the discrete time system is also stable, or whether the stability depends on the sampling time, right? So here first of all so there were two methods we have introduced for the discretization. First is the Euler's method, and where we have approximated this derivative part by that method, Another method is when we consider the signal u as a piecewise constant signal between the two sampling instant, and then we computed another discretization form of the continuous time system. So here, first of all, we'll do the sampling using the Euler method at two different sampling time, 0.5 and 0.1, and we see whether the system is state stable or unstable given the stability or instability in the continuous time domain. So you can quickly verify that the eigenvalues of the continuous time A matrix lie on the left hand side and on the real axis. So it is clearly an internal stable system, right? Now if we sample it using the Euler's method at the sample time t is equal to 0.5, this would be the A matrix in that case. Sample time multiplied by the A matrix plus an identity matrix of the appropriate dimension. So we obtain this AD. After putting this t is equal to 0.5, the continuous time A matrix and the identity, we obtain this A of t. Okay. Now computing the eigenvalues of this AD matrix, we see that one of the eigenvalues is inside the unit circle, while another eigenvalue is outside the unit circle. So if I sample my continuous time system at 0.5, we notice that the system is no longer a stable system in the discrete time domain. Now verifying at t is equal to 0.1, we see this AD matrix, and computing the eigenvalues, we notice that both the eigenvalues are in fact inside the unit circle. So at one sample time t is equal to 0.1, it is a stable matrix, or it is still a stable system. For another sample time, which is a bit on the higher side, we see that the system is no longer a stable system. And you can also parameterize the stability in terms of the sample time by solving this last equation in terms of t and determining the condition on the t. So we see that for all positive sampling time less than 0.53, the discrete time counterpart of the continuous time system would always be stable. Right? This is what we have noticed, that once we have chosen capital T is equal to 0.5, which is greater than this value, then the system becomes an unstable system. Right? So now if we use another method of discretization, that is the second method, which is equivalent to computing the discretized system by using the C to D command in the MATLAB, which is the continuous to discrete time domain discretization. So you will notice that that state matrix, whatever the state matrix we would obtain, it would be stable for all the sample time. So this method, so one of the consequences or one of the motivation behind using another method of discretization is that the Euler method is the least accurate result, provides the least accurate discretized system, and this is also visible in determining the stability also. So this condition provides a very conservative estimate of the sampling time. Now for the more accurate discretized method, which is equivalent to the C to D command, we say that you would notice that the state matrix is always a stable matrix. Okay. So this is the last problem of this tutorial. So we want to comment on the stability of the system x dot is equal to ax, where A is given by this 5 cross 5 matrix. So here we would utilize the theoretical results we had discussed onto the slide number 53 and 54, which basically discuss the relationship between the stability, the Jordan forms, and the minimal polynomial. So if you recall that we had defined we have obtained one of the results for stability, that if the eigenvalues are on the left hand side and if some of the eigenvalues are on the imaginary axis or the origin, and corresponding to those eigenvalues which have the zero real part, if the Jordan blocks are of 1 cross 1, then the system is marginally stable. So first of all we will compute the eigenvalues of this matrix, then convert them into another canonical form which is called the Jordan forms, and we'll see that whether if there are some eigenvalues on the having the zero real part, if all the Jordan blocks are of 1 cross 1, then the system is stable. If it is not, then the system won't be a marginally stable. Equivalently, we have also defined in terms of computing the minimal polynomial, which is basically computing the roots of a polynomial of a degree lesser than the characteristic polynomial if possible. And there are some properties which needs to be satisfied for the polynomial being the minimal polynomial. So first of all we will compute the eigenvalues. The eigenvalues of this A matrix, we have the repeated eigenvalues at the origin, and the another eigenvalue is on -1. Okay, so for computing the Jordan form you can use this MATLAB command which is given by its own name, Jordan, and by the given matrix A. So this J matrix you would obtain. Now if you notice here we have 4 repeated eigenvalues at the origin and 1 eigenvalue at -1. So first of all we'll form the Jordan blocks. So the first block is this one, which is corresponding to 3 repeated eigenvalues at 0. Another Jordan block is with respect to -1, and the last Jordan block is with respect to the 4th eigenvalue at 0. So here we notice that at the repeated eigenvalues at the origin we have a Jordan block of 3 cross 3. So this system is not a marginally stable system. Okay. Now computing the minimal polynomial, first we write the characteristic polynomial s to the power 4 s plus 1 is equal to 0. So from here you would see directly we would obtain the repeated eigenvalues located at 0 and another eigenvalue at -1. Now with the procedures introduced into the lecture slides, we compute the eigenvalues, the minimal polynomial, and the polynomial which is minimal and satisfy all the properties we had introduced at that time is given by s cube into s plus 1. The degree of this polynomial is 4 while the degree of the characteristic polynomial was 5. So this is of a lesser degree, and this minimal polynomial again shows that we have 3 repeated eigenvalues at 0, which is equivalent to saying here into the Jordan blocks. Since the Jordan block is of 3 cross 3, so it is trivial or it is expected from the minimal polynomial that it would yield the not so simple eigenvalues located at the origin. Okay.